Okay, welcome back after the summer break. This is the first pre-seminar of the winter term, and we have so we are happy to have Antonio del Donno giving us some basics on quantum permutation matrices. Please.
Okay, hello everybody. Thanks for asking me to do this seminar on quantum permutation matrices. So first of all, I have a disclaimer. Okay. So I don't know much about quantum permutation matrices actually. So I actually learned about quantum permutation matrices since 2 days. So I started learning something on this on Sunday. Then yesterday, today I took a flight to come here to do some research and also to do this seminar. So probably some of the things that I'm going to tell you, in principle, will not be 100% correct. Of course, feel free to ask questions if you want, if you must. Okay, so let's start. My seminar is divided in 3 parts, so I will start talking a little bit about classical permutation matrices and quantum permutation matrices, just giving you some of the basic definitions that we need. Then I will move to this other interesting topic, which is the one about quantum isomorphism of graphs that are linked to this definition of quantum permutation matrices that I'm going to give. And finally, I will very briefly tell some rudiments about how quantum permutation matrices and quantum permutation groups are connected to the realm of quantum groups that many people here in the audience are interested in too. Okay, so let's start with classical and quantum permutation matrices. So let us consider endpoints, any set of endpoints that you can think about. So we define a permutation as a square matrix, sigma, living inside a space of n times n matrices that are made just from zeros and one. And we also want that these matrices satisfy the following 2 properties. So first of all, we want that the entries of these matrices are either zeros or 1. And moreover, we also want that each column and each row contains exactly 1, 1, and all of the other entries have to be 0. So these matrices represent elements of the symmetric group Sn of endpoints. And in particular, they are matrices of the fundamental representation of Sn on Cn. So let's take a look to an example. So we consider the canonical basis vector of R4 or C4 or whatever you want. And this matrix is sigma here. This is indeed a permutation matrix. We can see that all of the entries are 1, and we can see that we can take the sum of all of the elements. And we get 1 either if we go through columns or if we go through rows. So we only have 1, 0. We only have 1, 1, and all of zeros in each row and each column. And what this matrix does is, in particular, take elements of the canonical basis and permute, giving us other vector of the same canonical basis and so on. Okay, so what's the thing with quantum permutation matrices? So the idea is to try to generalize the previous definition of classical permutation matrix to non-commutative projection that satisfy somehow the same combinatorial rules. So I'm going to go straight with the definition. Let us fix a natural number n. Let us consider a complex Hilbert space. Whether this is finite dimensional or not, it's not important at this stage. And we also consider the set of bounded linear operators on this Hilbert space H. So we define a quantum permutation matrix as a matrix, an n-dimensional square matrix made up of entries that are bounded linear operators on this Hilbert space. Call those entries U and J, with I and j ranging from 1 to n, such that the following 2 properties hold. So first of all, we want that each of the entries, U and j, is the Hermitian conjugate of herself, and we also want these matrices to be projectors. So in other words, we want that the square of each of the entries is equal once again to the matrix that we started with for each I and j ranging from 1 to n. Another technical property that we require is that whenever we consider the sum for k that goes from 1 to n of uak, or the same for ukj, we have to get 1 for all I and j ranging from 1 to n. So this means exactly that we want that if we take the sum over each row or over each column of our quantum permutation matrix, we are getting 1. So let us consider an example, not an example, let us maybe write down explicitly how a quantum permutation matrix looks like. Is essentially what you can think coming from the definition. So we have n times n matrices that are made up by bounded linear operators on a Hilbert space, or in particular, in the finite dimensional case, we can think about those entries uij as submatrices that build up our new matrix. So those are essentially are element of the bounded linear operators over the direct sum of n copies of the Hilbert space with itself. Yes, sure.
Second condition,
Yep.
why don't you want I equal to J? Like, seems that the two sums are kind of independent, right?
So let me think about it. So for all I and j that go from 1 to n, why don't we want I to be equal to j?
No, so you said with I not equal J, right?
Yes,
I'm just wondering why this is needed.
I.
Okay. This makes sense.
Okay, so for all ij, it's not that I has to be different from j. Okay, so sorry, maybe this is a typo. Okay. Okay, so forget about I different from j. We can take whatever we want here, I and j, of course. I mean, why not? Indeed, the sums are independent. And so maybe let's go on. So intuitively, we have that quantum permutation matrices are permuting n copies of the Hilbert space H, like how usual permutation matrices permute n copies of C. And if H is a complex finite dimensional Hilbert space of dimension D, we have, as I was saying before, basically that those quantum permutation matrices are n times n matrices whose entries are D times D matrices themselves. Okay, let's write down a very short example of a quantum permutation matrix. So let us fix H to be C2. So we consider this matrix here. And this is indeed a quantum permutation matrix. So as you can see, all of the assumptions that we require, according to the previous definition, are indeed satisfied. So if you take the sum over each row or over each column, we still get the identity, and one can check that all of the entries that we have inside this matrix, all of the uij's, in other words, are indeed projectors and are also Hermitian conjugate of themselves. Okay, indeed, this is what I was saying now. Okay, we have this lemma telling us some orthogonality conditions that quantum permutation matrices have to satisfy. So in particular, we have that for any quantum permutation matrices U that we write with entries uij, we have this condition here to be satisfied. And I'm quite sure that now I has to be different from J, right? So maybe this is why I was switching the two things. So here we really want that I has to be different from J. Okay, this should be a general property that projections have to satisfy. And yeah, so a remark is that in the case of C-star algebras, if one has self-adjoint idempotents P1, P2, that sum to 1, then necessarily one has that the product of the two has to be 0 for each I non equal to J. But if we don't consider necessarily C-star algebra, but we just consider star algebras, the situation is a little bit different. For example, we have a triple of projection that sum to 1 that still commute, but quadruples need not to commute in general. So in the definition of quantum permutation matrix in the realm of star algebras, usually we have that family of projection need not to be orthogonal mutually if they sum to 1. And this means that the result that we state here as a lemma in the general context of star algebras has to be assumed as a point of the definition, basically. Okay, so let us see how we can link quantum permutation matrices to classical permutation matrices. Under which condition, in particular, starting from a quantum permutation matrix, we can recover a classical permutation matrix. So in particular, we have that any quantum permutation matrix whose entries are bounded linear operators on a one-dimensional Hilbert space is indeed a classical permutation matrix. And this follows because essentially what we have is that the entries of these matrices are real scalars. And by the orthogonality lemma that we just cited in the previous slide, we have that we have only one non-trivial entry for each of the uijs that we have inside the quantum permutation matrix. So we recover a classical one. Another point is that if we assume the entries of a quantum permutation matrix U to be commuting bounded linear operators on a finite d-dimensional Hilbert space, then we can find some n-dimensional matrices with coefficient in C, such that the original quantum permutation matrix U is unitarily equivalent to this matrix here. So we have a diagonal matrix built up with these n-dimensional matrices over C. And so basically here we are recovering once again that we are building up n-dimensional matrices made up by d-dimensional matrices over C. And this is a way to produce, again, a classical permutation matrix starting from a quantum permutation matrix. More on this on the next slide. And another condition is that if we consider a quantum permutation matrix and we fix n to be smaller than 3, for example, then one can show that in this case all of the entries of a quantum permutation matrix commute. So in particular, if H is a finite dimensional Hilbert space, the result that we cite here in the second bullet point of this list continues to hold, and so in particular we also get that such kind of quantum permutation matrices are indeed classical permutation matrices. Okay, so maybe I have this small example here, which is basically a way to show a little bit more clearly the second point, how it works. At least I tried to do it by myself, so it can be wrong, but at least I tried, so let's see. So let us fix n to be equal to 3, and let us fix again h to be c squared. So the dimension of h is 2. And we consider two classical permutation matrices, two 3x3 classical permutation matrices with values in C. Then we define a quantum, we define another object which we would like to show that is a quantum permutation matrix that is built up in this way. So we are considering this tensor product of sigma 1 with E11, where E11 is understood as the usual matrix that comes to your mind. And the same we do with sigma 2. Okay, so what we get here is something that lives inside the space of three-dimensional matrices whose entries are bounded operators over the Hilbert space H, and this is isomorphic to the three-dimensional matrices of which entries are two-dimensional matrices over C. So the entries of U are indeed provided by this decomposition here. So we have this diagonal matrix with sigma 1 and sigma 2. And one can check that the entries of U commutes. And moreover, what one gets is that taking the sum over J or the sum over I, we are recovering once again one of the two assumptions that we use in order to define quantum permutation matrices. So what I tried to show here is that we start with two classical permutation matrices. We take somehow a sum of those after tensoring with E11 and E22, and we are able to recover a quantum permutation matrix. And of course, you are free to read the slide from the bottom to the top in order to see how, starting from a quantum permutation matrix, you can indeed build up something which is expressed as a sum of two classical permutation matrices. Okay, hope this was clear. So the next point that I would like to discuss briefly is the notion of quantum isomorphism of graphs. So let's start with the very definition. So we fix once again a natural number n, and we consider H to be an Hilbert space. Then we consider two graphs. So we have gamma 1 and we have gamma 2. We consider these graphs in particular to be finite simple. So with this, we mean that we have no loops and we have no multiple edges. And we have a V that goes from 1 to n. So we are considering endpoints here for each of the two. So a quantum isomorphism matrix of gamma 1 and gamma 2 is a matrix built up with an n times n square matrix of bounded linear operators over an Hilbert space H, consisting of entries U and J, for I and J going from 1 to n, such that the following four assumptions hold. Okay, so we have somehow some kind of familiarity with this assumption that we are writing down according to the slides that I was showing to you before. So, for example, the first and the second one are indeed what you ask in order to have the definition of a quantum permutation matrix. Indeed, we can use quantum permutation matrices to generalize the notion of isomorphism of graphs. So, properties 1 and 2, as I was saying, are properties that you require in order to have a quantum permutation matrix, and this means that a quantum isomorphism matrix is indeed itself a quantum permutation matrix. And we also have these other two properties, 3 and 4, and with this notation here, I mean, so when you have this sim symbol with the 2 underline, you're meaning that from I and K, you have an edge that connects the 2 via the graph 2, and similarly for all the other ones. And here, of course, this is not a Q. This, you can see, this is a 1, not a Q. But the keyboard 1 and Q are very close, so this is an error that can happen. Okay, and so how can we look to properties 3 and 4 in order that we can actually remember those? Because otherwise they may look a little bit sketchy. So we consider the adjacency matrix of each of the two graphs. So let's call it AK, and the adjacency matrix of the graph gamma K. So we can prove, they proved, that the relations 3 and 4 hold if and only if UA1 is equal to A2 of Q. Okay, so equivalently, instead of remembering all of these two relations, we can just talk about the third bullet point of this list and have the same content from a mathematical point of view. Okay, so what else? If a quantum isomorphism matrix exists between two graphs, we call these two graphs quantum isomorphic. And it's a surprising fact that we have some graphs that are not isomorphic, but are quantum isomorphic. I don't know, I'm not able to provide an example of this right now, at least if I remember this correctly, but I have an example of graphs that are quantum isomorphic. So we consider this graph here. So we have a graph gamma with 4 vertices and with the edges that I outlined here in this picture. So we consider P and Q to be two elements, two bounded linear operators of an Hilbert space H, and we consider these two elements to be projectors. So we have that matrices of this form here. So you can take a look to this matrix a little bit if you want, are quantum automorphism matrices of gamma. So where quantum automorphism matrices, of course, relate to the same definition that I was giving before. The only difference is now that we are using the same graph twice instead of two different graphs. And so in particular, the matrix that I wrote here is a quantum isomorphism matrix of the graph that I was presenting in the last slide. Okay. So we have some open problem with graphs that I can only state, unfortunately, because I didn't have much time to solve all of this problem by myself, but of course. So given a finite simple graph gamma, is there a quantum automorphism matrix of gamma whose entries do not all commute? In such case, we say that gamma has quantum symmetries. Okay, so here I try to sketch a little bit out an example by myself. So the adjacency matrix of a complete 4 vertices graph K4 is the one that you can read here. And we may write this as different of two matrices. So we have the matrices with all 1 and the identity. Okay, so we just consider this as the subtraction of these two. So for a quantum permutation matrix, since the column and rows, some of U are 1, we also have that the following property holds. So we can take the product of U with J or the same of J with U, and we get back J once again. And so this implies that we can actually do the same with U because of the other component is the identity, of course, and if we take the identity with A is of course equal to A times the identity. So we have that U times A is the same as A times U. And so this means that every 4 times 4 quantum permutation matrix is a quantum automorphism of K4. Okay. So in particular, this means that also those matrices that have non-commutative entries are, and so in particular, we say that here we have in particular an example of a finite simple graph whose entry is not necessary, where we have a quantum automorphism matrix of whose entries are not all commuting. And so in particular, we see that this graph has indeed some quantum symmetries. Okay, so some other problems that I just state here. So can we find an asymmetric graph gamma? So in particular, a graph such that the automorphism group is trivial, that admits a quantum automorphism matrix with sum of diagonal elements. Okay, this is interesting because such an example would be purely a quantum symmetric situation with respect to the definition that I was giving to you before. Another question is that if we have two simple connected asymmetric graphs that are not classically isomorphic, can we still have that in some kind of situation those are quantum isomorphic? As I was saying before, so we have some graphs that are not isomorphic from a classical perspective, but are quantum isomorphic, so maybe we can have the same here in this very particular scenario. And so some also explicit small example would be great to find. So another question is that can we find two non-isomorphic graphs with less than 24 vertices that are quantum isomorphic? And also another question would be to find the smallest example known of this kind of framework. And yes, this will probably be interesting for some computational understanding of quantum permutation symmetry. Okay, sure. Say it again, sorry?
Big problem.
Ah, really? Okay, so in 3 years, everyone solved everything. Okay, yeah. Okay,
Pretty well.
okay.
And that the graph can also solve the middle one.
Oh, nice.
Asymmetric graphs that are not isomorphic, but they're quantum isomorphic.
Thank you very much. So I don't have to do it. You already did. You already did it. No, okay, so the reference that I will provide afterwards is a reference from 2022 or 2023 by Maurice Weber, and he's stating these as open problems. But okay, thank you for the observation. Okay, so finally we move to the very last part of this small presentation, which is somehow an attempt to build up a little bridge between quantum permutation matrices and in particular quantum permutation groups with quantum groups. I'm not going to go inside the details here, but the story goes as follows. So Voronovich defined compact matrix quantum groups and showed that this class naturally generalizes the class of compact groups. And here I'm giving a slightly simplified version of the definition of a compact matrix quantum group. So we have a pair AU, where U has entries UAJ, such that A is a unital sister algebra which is generated by the elements UAJ in A. Moreover, we also have that U and the corresponding Hermitian conjugate are invertible matrices in the space of n-dimensional matrices with entries on A. And we also want that this map delta from A to A tensor A, given with this definition here, is a star homomorphism. So Voronovich proved a Gelfand-Naimark style theorem holding up for compact matrix quantum groups. So if the C-star algebra A that we are assuming here to be the one that we are using in the definition of compact matrix quantum group is commutative, then A is isomorphic to the algebra of functions CG on some compact matrix group inside the GLN C. So we have some very relevant examples of compact matrix quantum groups, as probably everybody inside the audience knows. For example, one can consider a C-star completion of OQSU2. And yeah, so let's see what the role of quantum permutation matrices and groups is here. So in the 90s, a quantum version of the symmetric group on n elements was proposed, and this is in particular given by the universal sister algebra on generators UIJ, such that we have the properties that I'm showing here to hold, and you can recognize this property to be very much alike the one that I was suggesting for the definition of a quantum permutation matrix. So indeed, this is the sister algebra, the universal sister algebra generated by the entries of a universal quantum permutation matrix, if you want. So if we add the commutativity of all of the generators to this sister algebra, we obtain a commutative sister algebra which is isomorphic to the algebra of continuous functions on some compact space. So the space in question is indeed the symmetric group, okay? So we have a reasonable quantum counterpart of Sn starting from this reasoning here. So the problem of understanding quantum permutation matrices, if you want, can be linked to the understanding of the representation theory of this universal sister algebra defined in terms of these elements U, A, J. So quantum permutation matrices are indeed star representation of the latter. So this was just a little bit to tell you how one can move from quantum permutation matrices to the theory of compact matrix quantum group. And with this, I think that I will be finishing. So thank you for your attention. This is the reference that I used to prepare this very short talk. I remember to you in 2 days, so be very kind with me. And thank you for your attention again.
Thank you for this nice talk.
Thank you.
Do we have some questions or maybe answers also?
Good one. Go ahead.
Some sort of non-commutative geometry for these quantum groups.
Say it again, sorry, what
Some
about?
type of non-commutative geometry for these quantum groups, a differential calculus, what? Question. Ah, wait, not using the microphone.
Okay, I don't know. I don't know. I don't have any clue. So do you have some thought about it?
A little bit, but okay.
Do you want to discuss with the audience?
Maybe now is not the okay.
Okay.
There are for some of these unitary quantum groups, you can put differential calculus.
Oh, very nice.
But yeah, okay.
We can talk about it afterwards, surely.
More questions?
Was the first slide equal?
Yes. Let's go back there so that everybody understands how my feeling is about the questions. Okay.
Not so much a question, but maybe in comment. So I
Okay.
mentioned the open problem was solved. Like,
Let's go back there so that everybody can read.
yes. Yeah, so the question here was, can we find an asymmetric graph which has quantum automorphisms? Okay,
Yeah.
we have examples of that. Still an open problem remains. There's a notion of quantum orbits of, at least if you have quantum permutation groups acting on things, you have orbits. So you have a notion of a quantum automorphism group of a graph being transitive or not. And one open question that we still have is, can we find a graph which is asymmetric, but its quantum automorphism group acts transitively even?
Okay.
And like the way we approach it in our construction, you can never get that because we really like encoded certain orbits with colors, and that's really essential to the construction. So you really need a different construction. So if people still want a nice open problem, maybe you
Okay.
have something to work on.
Maybe.
Yeah. Yeah, we know it has to have at least 16 vertices. But other than that, we have the example on 24 and we have no idea where it's going to be. Yeah.
Yeah, I failed to cite this here, but yes, also on the reference that I was studying with, it was referring to this 16, but it's just a lower bound, right? It's not that we already know that this has to be the list in some sense. Okay.
Right. Thank you.
Yeah. Yes.
Okay, more questions? If not, let's thank the speaker. Now there's a short break and then the main seminar.